Hello everyone, in this video we will finish the chapter 11. In the previous video we defined the Taylor and Maclaurin series by using the theorem written here. The Taylor series expansion of the function f at some number a is written here. In this theorem, our aim is to prove the formula for the coefficient Cn. How can we find Cn, which is equal to actually the nth derivative of f at a over n factorial? It can be found easily by just taking the derivative of the power series representation of the function f. The Taylor series expansion is written here, and our aim is to find a formula for actually the coefficients of the terms which are Cn. And the Maclaurin series of the function f is founded by writing 0 for a. It is a special case of the Taylor series. It is actually a Taylor series expansion at 0. So for finding the coefficient formula for in the definition of Taylor series expansion of the function f, first we write explicitly the Taylor series expansion in this form. You see, if you write natural numbers including 0, you will obtain the terms like that: c0 plus c1 times x minus a, which is obtained by writing 1 for n in the formula written here. And firstly, if you write a for x in this equation, you will obtain c0, which is equal to f of a, because every term except the first term c0 becomes 0 if you write a for x. Okay, and this is the first formula for the first coefficient. c0 is equal to f of a. And to find c1, we take the derivative of the equality written here, which is the explicit expression for the Taylor series expansion of the function f. If you take the derivative, first derivative of f, the derivative of constant is 0, the derivative of the second term is c1, the derivative of third term is 2 times c2, because we have the number 2 for the power of x minus a, and its derivative becomes 2 times x minus a. Also we have the derivative of inner function, namely x minus a. Its derivative is 1, therefore we don't need to write 1 here. And similarly, you can take the first derivative of the next term, which is 3 times c2 times x minus a square, and so on. So in this equation, if you put x is equal to a, so you can find the first derivative is equal to c1 at a, because all terms except c1 will be 0 if you put x is equal to a. And to find the formula correctly, we can write the derivative of f at a over 1 factorial is equal to c1. 1 factorial is equal to 1. Similarly, by taking the second derivative of the previous equality written here, the derivative of c1 is equal to 0. The derivative of next term is 2 times c2. The derivative of next one is 2 times 3 times c3 times x minus a times the inner function, if you remember from calculus 1. The derivative of next one will be this one, and so on. You can see easily the derivatives. And if we put x equal to a for x, you will obtain the second derivative at the number a, because we write a for x is equal to the constant on the right side of the equality, because every term here will be 0 if you write a. And this one can be written in this form by writing the number 2 in the denominator on the left side of the equality. Actually we have 1 times 2, which is written as 2 factorial. And similarly, by taking the third derivative of the previous equality, the derivative of 2 times c2 is 0. The derivative of next one is 2 times 3 times c3. The next one is equal to 2 times 3 times 4 times c4 times x minus a, and so on. And if you write a for x, you will obtain the third derivative of f at a is equal to the constant, and this can be rewritten as the third derivative over the numbers in front of c3, and we have a multiplication of the numbers 1, 2 and 3 actually, and it can be written as 3 factorial and so on. By taking more derivatives, you will find the third derivative, the fourth derivative at a over 4 factorial will be equal to c4 and so on. Generally, by applying induction, you will obtain cn will be equal to the nth derivative, because we have the same numbers for the degree of the derivative of f and the index of c, and in the denominator we have also same number. Therefore we write n factorial, you can see, by applying the induction. And generally you can find explicit formula for the Taylor series expansion of the function f if it can be represented by a power series. Namely, a function can be represented by a power series by using the formula written here according to the interval of convergence for the power series. This is the proof of the coefficient formula for the Taylor series expansion. And you know, Maclaurin series can be found by writing 0 for a in the definition of Taylor series. So let's do an example for that to understand very well. So find the Maclaurin series of the function fx is equal to e to the power x and its radius of convergence. According to the formula, we have to find first the coefficients for the Maclaurin series. It is written here. Namely, we have to find the nth derivative at 0, and we can find easily. So you know, the first derivative of exponential x is equal to itself, the first derivative, f prime x is equal to e to the power x, if you remember. The second derivative will be itself, the third derivative will be itself. Namely, we have the same function for every derivative for exponential to the x. Therefore, generally we write the nth derivative of f is also equal to e to the power x, and you know, the Maclaurin series can be obtained by writing 0 for a. Therefore, we write 0 for x, e to the power 0 becomes 1. So according to the formula for the Maclaurin series for the coefficient, the nth derivative of f at 0 will be 1. Namely, every coefficient will be 1 over factorials. So if you write 1 for this, we get x to the power n over n factorial, and explicitly you can write the terms of this power series representation for exponential to the power x. Interestingly, it is equal to e to the power x, and this expression is valid for every real number for x. You can find e to the power x for every x by using this power series representation. Why? Because if you want to find the radius of convergence or the interval of convergence, you know, we apply ratio test or root test, if you remember. So the general term of this power series representation is x to the power n over n here. So according to the ratio test, we have to find the ratio of the terms an plus 1 over an in the absolute value. If you remember, an plus 1 is x to the power n plus 1 over n plus 1 times 1 over an is n factorial over x to the power n. X to the power n plus 1 can be written as x to the power n times x, and by simplifying x to the power n, similarly n plus 1 factorial can be written as n plus 1 times n factorial, and we can simplify n factorials. So we have in the numerator just x in the absolute value over n plus 1. You know, n is a natural number, therefore n plus 1 will be positive, therefore we don't need to write the absolute value for n plus 1. And we have to find the limit of this expression as n goes to infinity. Limit n goes to infinity of this one, x over n plus 1. You know, the variable of the limit is here n. Therefore, we consider the variable x, which is the variable of the function, as a constant. Therefore, any constant over infinity, if you write infinity for n, any constant over infinity becomes 0. Therefore, its limit will be equal to 0 by considering the variable x as a constant for the limit. And if you remember the ratio test, if the limit is less than 1, so it is convergent. And you see, whenever we write any variable for x, any real number, we have always 0 for the limit of the ratio of the terms written here, and it is less than 1. Therefore, we say the power series is convergent for all real numbers, which means the Maclaurin series for exponential to the power x, which is very important function in applied science, can be written as 1 plus x over 1 factorial, x squared over 2 factorial, and so on. We have infinite series for exponential x at 0. Okay, and as a result, we can write the Maclaurin series of exponential x is equal to x to the power n over n factorial for all real numbers. In particular, if we put x is equal to 1 in this equation, we obtain the following expression for the number e as a sum of an infinite series. This is a special number which is called the natural logarithm number, and its expression by using the power series expansion for exponential x can be in this form: 1 plus 1 over 1 factorial, 1 over 2 factorial, plus 1 over 3 factorial, and so on. Okay, you know, actually this is approximately equal to 2.71 and so on. It is irrational number, and another expression for this special number like pi can be found by using the Taylor series expansion or Maclaurin series expansion, which is very interesting. So find the Taylor series for the same function at a is equal to 2. You know, in the previous example we found the Maclaurin series, which is the Taylor series, actually at a is equal to 0. So now we will find expansion for e to the power x Taylor series expansion at a is equal to 2. You know, the nth derivative of f is equal to e to the power x. The nth derivative, you know, in the previous example we found the nth derivative of x is equal to e to the power x. So we find the Taylor series expansion at a is equal to 2, writing 2 for x, we obtain a squared. And so writing a is equal to 2 in the definition of a Taylor series, so we obtain, the nth derivative of f at a over n factorial, and a is equal to 2 times x minus a is equal to 2, x minus 2 to the power n, and we know the nth derivative of f at a is equal to e squared from here. Therefore we have e squared over n factorial times x minus 2 to the power n. Okay. So another important function is sine x. Let's find the Maclaurin series for sine x. We arrange our computation in two columns as follows. First we have to find, if you remember the Maclaurin series, we have to find a general formula for the nth derivative of f, and by writing 0 for x, we find the value of nth derivative of f at 0, and we find the Maclaurin series of the function f. For this, let's write first f of x is equal to sine x. The first derivative is cosine x, the second derivative is minus sine x. The third derivative is minus cosine x. The next one is sine x, and so on. In here, our aim is to find a general idea for the nth derivative of f by writing 0 for x. Actually, what is the general formula for the nth derivative of f, which is sine x, at 0 to find the Maclaurin series? Okay, when we write 0 for x, which is the first coefficient, f of 0 is equal to 0 because sine 0 is equal to 0. The first derivative is equal to cosine x. When we write 0 for x, we obtain 1. Cosine 0 is equal to 1. The second derivative is minus sine x, so we write 0 again. We have minus cosine x for the third derivative. Therefore, cosine 0 is 1. We have minus 1, 0. You see, first term, third one, fifth one, seventh one, and so on. Actually, we have here x to the power 0. This one is x to the power 1 in the formula. This one is x to the power 2. This one is corresponding to x to the power 3. This one is x to the power 4, and so on. Normally we have x minus a to the power n, but we find the Maclaurin series, therefore we write 0 for a, and they become x to the power 0, x to the power 1, x to the power 2, x to the power 3, and so on. For even powers, we have always 0, you see. For odd numbers, we have 1, minus 1, 1, minus 1, 1, minus 1. Therefore, the derivatives, since the derivatives like this repeat in a cycle of 4, we can write the Maclaurin series as follows. We have f of 0 is equal to 0, as I said. This one becomes 0, the first term becomes 0. Therefore, we are interested in odd numbers for the powers of x. So x1 is corresponding to 1, therefore we write x minus, because the next one becomes 0 because of the equality written here. The second derivative at 0 is equal to 0. So directly we are interested in x to the power 3, named actually its coefficient. It is the third derivative at 0 over 3 factorial, and third derivative is equal to minus 1. Therefore, we write minus 1 over 3 factorial times x to the power 3, and it is rewritten as minus x3 over 3 factorial. and fourth derivative, the coefficient of the x to the power 4 becomes 0 from here. Therefore we are interested in the x to the power 5, actually its coefficient, and we will have 1 for the fifth derivative of f at 0. Therefore we will write 1 over 5 factorial times x to the power 5, and so on. Therefore the Maclaurin series for sin x at 0, sin x, will be in this form. And using the terms here, you can find easily the general term. It is alternating series. Therefore we write minus 1 to the power n from 0 to infinity. And we have odd numbers for the power. Therefore we write x to the power 2n plus 1 to n plus 1 factorial, since we have odd numbers. Similarly, you can find the Maclaurin series for cosine x. This is your homework. Please do this homework at your homes. You will follow the similar way of sin x to find the Maclaurin series for cosine x. So let's find the Maclaurin series for the function x times cosine x. So we know already the Maclaurin series for cosine x. Therefore just writing its Maclaurin series for the function f using this equality, we can find easily for the function f its Maclaurin series x times cosine x. Instead of cosine x, you write its Maclaurin series written here, and multiplying it by x, we obtain, actually we have x to the power 2n by but we multiply this x to the power 2n by x, so we have x to the power 2n plus 1, and we find the Maclaurin series for x times cosine x. And similarly you can find, we know already the Maclaurin series for 1 over 1 minus x from 0 to infinity. It is actually obtained by the geometric series. It is valid if the absolute value of x is less than 1. Therefore the radius of convergence will be 1. And you know, in the previous examples we found a to the power x, so it is valid for all x, for all x. Namely, you can write any real number instead of x, e to the power 3, e to the power 4, and so on. And sin x is valid for every x if you apply the ratio test for the general term. You will obtain its limit as 0 for every x. Therefore it is valid for all real numbers. Similarly, we can say the same thing for cosine x. And we found arctangent x. We find the Maclaurin series of arctangents in the previous examples, you know, by using the mean formula, which is 1 over 1 minus x is equal to the power series written here. And we found also ln 1 plus x in this form, and it is valid if the absolute value of x is less than 1. And also you can find the power series representation, actually Maclaurin series representation for 1 plus x to the power k. It is a special case of the binomial expression, binomial expansion. You can find easily, just finding a general formula for the nth derivative of f. So how can we use them in applied science? For example, find the sum of the series 1 over 1.1 times 2 minus 1 over 2 times 2 squared plus 1 over 3 times 2 to the power 3, and so on. So first let's find the general term of this series. by using the sigma notation, we can write the given series as it is an alternating series. Therefore, we write minus 1 to the power n minus 1, or minus 1 to the power n if you start at 0. Of 1 times, in the numerator we have the same number 1 times, for example, when we write 1 we have 1, when we write 2 we have 2, we have 3 and we have 4, therefore we write n, and we write 2 to the power n for the other term in the multiplication and the denominator. For example, when we write 2 we get 2 times 2 factorial, which is corresponding to the second term in the denominator. Therefore, it is the general term of this series. And by rewriting to use a formula in the table to find directly its sum if it is convergent. So we write it is minus 1 to the power n minus 1. So we write this one as 1 over 2 to the power n, this one over n. So then from table 1 we see that this series matches the entry for ln 1 plus x with x is equal to 1 over 2. When we look at the formula for ln 1 plus x, we see minus 1 to the power n minus 1 we have here, and x to the power n over n. We have, instead of x, we have 1 over 2 to the power n over n. Therefore, from the formula, and 1 over 2 is satisfying this equality, therefore we can use this formula. So this is equal to, from the formula of ln 1 plus x, we write ln 1 plus 1 over 2 is equal to ln 3 over 2. And also we can find the limit by using the Taylor series expansion or Maclaurin series expansion for some functions. You see, evaluate this limit by using the Maclaurin series expansion for e to the power x. If you remember, it is equal to 1 plus x over 1 factorial plus x squared over 2 factorial and so on, and we have minus 1 and minus x over x squared. So from here we can simplify plus 1 and minus 1, and we can simplify, this is equal to x minus x becomes 0, so just we have x squared over 2 factorial plus x to the power 3 over 3 factorial and so on over x squared. And by applying the division for every term in the denominator, we have x squared over x squared becomes 1, therefore we have 1 over 2 factorial. X cubed over x squared becomes x, x to the fourth over x squared becomes x squared over 4 factorial, and so on. And if you write 0 for this, we can find easily 1 over 2, because power series are continuous functions. Normally, if you write 0 for x here, we have 1 minus 1 is equal to 0, so this is equal to 0. We have undefined form, indefinite form, 0 over 0. So to get rid of 0 over 0, we use the Maclaurin series expansion for e to the power x easily. And then we cannot take the integral of a special function by using the basic formulas for this function, e to the power minus x squared dx cannot be found by using the integral formulas, basic integral formulas, but by using the Maclaurin series expansion of e to the power x, which is equal to the sum to infinitive and is equal to 0, x to the power n over n factorial, you know, n factorial. So instead of x we will write minus x square. Instead of x we will write minus x square. Minus x square is equal to, from here, for x we write minus x square, and this is equal to, you know, we have minus here, so writing this as minus 1 to the power n separately, so we have x to the power 2n over n factorial. Explicitly it can be written as, if you write 0 for n we get 1 for here, so we have 1. If you write 1 for n we have minus. If you write 1 for n we have x squared over 1 factorial. Similarly, plus, if you write 2 for n we get the third term. We have plus 1, therefore we write plus. If you write 2 we have x to the power 4 over 4 factorial over 4 factorial, sorry, 2 factorial minus x to the power 6 over 3 factorial, and so on. Okay. So for the function e to the power minus x squared, we have a Maclaurin series or Taylor series expansion. So in order to find its integral, we will benefit from this expansion. It is equal to the integral of this one, dx is equal to x minus x cubed over 3 plus x to the power 5 over 5 times 2 factorial minus x to the power 7 over 7 times 3 factorial, and so on. That's it. Just using the Maclaurin series expansion for e to the power x, we have a result for the integral of e to the power minus x square. You can find a numerical value approximately by taking some finite terms here, and you can find a numerical value for e to the power for the integral of e to the power minus x. It is mostly used in applied science, in applied mathematics, the Taylor series expansion and Maclaurin series expansion. Okay, thank you, and please send your questions by email, or take a photo and send your photos to me by email or to my phone. Thank you very much.